convergent, and those are obviously some confusing, they're close confusers, so this can get a little confusing. I'm going to try and simplify it as best as I can. All right, here's the deal. The reason why we're talking about this is because it's going to come up later when we do this thing called an interval of convergence, but we're not there yet. So now we're just learning about the idea of something being absolutely convergent. Okay. So when we see absolute, it's connecting with this idea, if you will, of absolute value. So if we have a series that converges and all the terms are positive, we will say that it's absolutely convergent. Okay. If we have a series that has some terms which are positive and some terms which are negative, all right, it may converge, and we can figure that out by the alternating series test, but it may not be absolutely convergent. And if that's the case, then we call the series conditionally convergent. So what do we mean by that? Okay, here's the deal. This series right here is an absolutely convergent series. Why do we know that? Because we're going to ignore the alternating part. Because we have -1 to the n plus 1, this is going to be n minus 1. This is going to be a situation where we have the first term will be 1 over 1 cubed, and then the next term will be negative. Right? It'll end up actually being 1 over 8, but it will be negative because when n is 2, 2 minus 1 is 1, and -1 to the first power is -1. But then the next term is positive, so we end up having 1 over 27. But then the next term is negative, we have 1 over 64. And this just keeps going and going and going. So what we're really looking at here is what's going on with the, if we just look at the positive terms. Right? So in essence, we're going to think of this as just 1 over n cubed. And if we just look at that 1 over n cubed, this converges, right? Because it's a p-series where p is equal to 3, and if the p is greater than 1, then this series will converge. Right? So because when just the positive terms converge, that's an absolutely convergent series. Now let's compare that with this series right here. If we do the same thing and we look only at the positive portion of this, so we're going to ignore the alternating part. What do we have? Well, we just have 1 over, instead of -1, we have 1 over the cubic of n. We know that we can turn that into n to the 1/3 power. Right? This is one of our algebra rules. This is also a p-series. But this diverges. Because it's a p-series where p is equal to 1/3, which is less than 1. And if p is less than 1, then the series diverges. So this series, initially, is an alternating series. We can actually do the math out using the alternating series test, where we see that the terms decrease in absolute value and everything. This series will converge. And it converges because it passes the alternating series test. However, it's not absolutely convergent. Why not? Because if we just look at the positive terms, then now the series diverges. So while the series will converge, it's considered to be conditionally convergent. Okay, over here, this series also converges by the the alternating series test. When we look just at the positive terms, we get a p-series which converges. So it is absolutely convergent. In essence, if we take away the negatives, it will still converge. If we take away the negatives over here, the series will no longer converge. So if we take away the negatives and the series no longer converges, it's known as conditionally convergent. If it still converges, then it's known as absolutely convergent. That's the idea behind absolute convergence. We'll do the examples in the next video.